In this video, I want to continue our discussion of how we can balance samples of treated and untreated individuals, and I'm going to talk specifically about how we can then use that to do matching, which allows us then to evaluate an average causal effect. So the example which we were talking about in the last video was the example of on-the-job training, whereby an individual either chooses to undertake on-the-job training or not. In other words, JI is equal to 1 or it's equal to 0. And we spoke about how we could actually stratify our treated sample. So by stratify, what I mean is what we could do is we could break up our treated sample into, let's say, subgroups, and I chose 4 subgroups just sort of arbitrarily. And the idea is that each of those subgroups has a particular average level of past year's sales. So we have a group with 10, one with 15, one with 20, and one with 25. And just to emphasize, this is for the treated group. And the idea is that what we would then do is we would compare this with sort of made up strata from those individuals who are untreated. So this bottom bar here represents those who are untreated, those who didn't choose on-the-job training. And what we could do is we could pick particular individuals to go into each of these subsamples, which essentially made each of these subsamples look very similar with those of the treated sample in terms of the past year's level of sales. So the idea is that what we've essentially done is we have matched each of these subsamples across, or at least in terms of, the past year's level of sales. And this matching then, what this allows us to do is we can actually evaluate the difference in mean level of sales between these two groups, and in that circumstance, the mean level of sales across each of these different groups might represent some sort of average causal effect. And when we take a sort of weighted average of each of these individual average causal effects across the subgroups, that might then give us some sort of approximation of the average causal effect. So we've seen in the past example that stratification across covariates, in other words, creating these different strata within our sample, within our treated sample, and then making up corresponding untreated individuals who have similar values to the covariates, can in some ways allow us to evaluate an average causal effect, even though we don't have experimental design. And the example which we gave here was whereby we only had one covariate, where the covariate represented the sort of past level of sales of an individual I. And the idea here was that essentially when we were just comparing the treated group with the entirety of the untreated group, we were unwittingly actually capturing some of the differences in their innate goodness as salesmen, because we might hypothesize that those that were perhaps better salesmen might be those that were more interested in and actually chose to undertake the on-the-job training in the first place. So we'd actually be overestimating the effect of the on-the-job training in that circumstance. And intrinsically, there were some problems with this stratification. One of the problems is it was completely arbitrary that I chose to break up my sample into a sample of 4 subsamples. I could have chosen 10 subsamples, or I could have chosen to have only one subsample, which is the actual sample. There is no sort of sensible answer necessarily for at what level I should stratify my sample. I mean, you could say, for instance, I would do it at the individual level, but that in turn poses some problems when you're trying to match across covariates, which we'll come on to in a minute. Intrinsically, we were dealing here with a continuous variable, and as I've mentioned, this problem we're dealing with a continuous variable is that essentially we don't know how to stratify our sample. That would be easier if we were dealing with a binary variable at least, because that can only take on a value of 1 or 0, so it's much easier to think about how I could make up subsamples in the untreated, which would then be comparable with those of the treated. But the real problem comes in here when we are dealing with many different covariates. So xi here is what we say is highly dimensional. In other words, it represents a number of different covariates which we need to match across. And I want to illustrate this issue by means of an example. Continuing with the same example which we've been running with, is let's say that we still have some sort of suspected difference in the level of past year's level of sales of each individual I. So we think that that's certainly a factor in determining whether or how well that salesman actually performs. We might also suspect that motivation of an individual also has something to do, and that's not necessarily exactly the same thing as the past year's level of sales, because individuals become motivated or demotivated at different points in time, so they don't necessarily represent the same thing. They're probably highly correlated, but they don't represent exactly the same thing. So perhaps what we have is we have some data on their level of motivation as sort of collected from, let's say, that individual's appraisals. So what we might do here is we might then stratify our sample across both of these variables. So perhaps we choose 4 subsamples where if we assume motivation is at least measured to some degree in a continuous manner. Then for our group who were treated, we can see quickly that because we stratified in 4 subsamples across 2 variables, we're going to have 4 by 4 subsamples. In other words, we're going to have 16 subsamples, which we're going to need to make up corresponding subsamples in our untreated population. So the idea is that what we would try to do is we would try to come up with corresponding subsamples within our untreated population. So this is the sample of individuals who were untreated. And the idea again is that what we would do is we would come up with 4 subsamples across the past year's level of sales and 4 across an individual's motivation. So the idea here is that what we could then do is then, if we could find individuals who were treated in, let's say, this top left corner of our sample, call that A, we could then compare their mean level of sales with the level of sales of those individuals in the corresponding untreated population. And if we thought that the past year's level of sales and motivation were the only 2 important variables in determining how well an individual fares in terms of sales, then we might think that a simple comparison means between these 2 groups might then at least approximate an average causal effect. And similarly, I could do the same thing with the second cell, so that would be cell B with, let's say, cell B primed in the untreated. And again, what we could then do is we could evaluate the difference in mean level of sales between these 2 groups. And we could do that for all of the different subsamples. And the idea then is that what we could then do is come up with an estimate of the average causal effect, which would be some sort of weighted average across the P subgroups, which would be a sum over, let's call this all P, of the difference in mean in each of the P subgroups. So comparing A with A prime, B with B prime, C with C prime, etc. Then an average causal effect across the entire sample might represent an average across each of these different differences in mean. So even though this provides a way in this quite simple example of actually coming up with an estimate of the average causal effect, the dangers of this method are quite obvious. One of the dangers is that essentially if we're dealing with data which is more highly dimensional, so perhaps we're dealing with 3, 4, 100 different covariates, then essentially each of these different cells which we're going to stratify our sample over are going to get smaller and smaller within our treated population. So when we're dealing with highly dimensional data, there may not actually be anyone who actually sits within that exact same cell within the untreated population. So in that circumstance, it may not even be feasible to stratify our data and then match the treated with untreated subsamples. And the reason for that is that what we call common support, in other words, the sort of values of the covariates in the treated population, may not necessarily overlap with the exact values of the covariates in the untreated population. And because there is this lack of overlap in common support, that will mean that we can't actually make up individuals or subsamples of individuals in the untreated population, which we can then compare directly with those of the treated. Another problem is that this is obviously computationally expensive. It's not necessarily that obvious when we're dealing with 2 variables, but when we're dealing with many different, in a lot of cases, continuous variables, it's actually going to be quite computationally expensive to actually come up with subsamples of the untreated and match them adequately with those in the treated population. Obviously, one of the solutions to both of these sort of issues is to aggregate groups. In other words, not to stratify your sample as heavily as we've done here, perhaps. Perhaps you might just stratify, let's say, twice across both of these two variables. But then what we have is we have the issue whereby we might not necessarily be comparing apples with oranges, because when you make groups bigger, intrinsically there is going to be some heterogeneity within those groups, which is going to mean that we're not necessarily comparing those individuals who are exactly the same in the treated group with those in the untreated group. So because of that, we might actually be unwittingly, by comparing the means between these two subgroups, actually getting some insight, not necessarily into the average causal effect, but into the differences in the covariates, which also affect the outcome variable, in this case sales. So I hope I've illustrated here the problems inherent with stratifying a data sample and then matching across subgroups in the treated and untreated populations, in that mainly the issue is here that this may not be feasible for highly dimensional data. What we're going to see in the next few videos is that by matching across a propensity score, this provides a means of actually removing this highly dimensional aspect of the data and still allowing us to come up with estimates of the average causal effect by doing a kind of matching on this propensity score.